2x plus 1 and 5x minus 4. When you start with these problems, you always start working from left to right. Negative 2x plus 1, y-intercept of 1, slope of negative 2. Let me just walk our slope. I go back and I read the domain. The domain tells me that I have to be everything less than or equal to 2. So in this case here, I go to where x is equal to 2. And it's less than or equal, so that means that's going to be a solid dot. And I'm going for numbers that are smaller than that, so that means I'm going to the left. And I erase those other ones. And that's the first part of the graph. Okay? Go to the next graph, the next equation down there. The next equation is 5x minus 4. Start at your negative 4. Up 5 over 1. Up 5 over 1. Up 5 over 1. Now, I know that on your grids it might have gone off the line. It's not a big deal. When we do the test on this stuff, I'll make sure that make my best effort to make sure things fit cleanly. And this one here, I'm looking for, once again, what happens at x equals 2. At x equal 2, it's here, but does that have to be a solid or an open dot? It's got to be open. So
open.
And if you are walking your spots like I did by just filling them in a little bit, if you go back and just put a big circle around it, that is fine with me. And once again, I'm looking for numbers that are larger, so I'm going the other way. Yeah, Caleb?
When we did, I don't remember which one it was, the graph yesterday, and it was like a table on sides and then what you learn like the next x. So like
When
when
it's
you
great.
start like that point at fraction.
Oh, I know what you're talking about. What's happening here in the graph is that as the numbers of x, once it gets larger than 2, it automatically jumps to this one. So it's never going to be at this point. It's going to be a little bit to the right of it, and up a smidge. It's just saying that, I'll get you in 1 second. It's just saying that if you're approaching this going from the top down, going from right to left, if you're descending down here, you're getting infinitely closer and closer and closer to x equaling 2. The very instant that x equals 2, it jumps to the other equation because that's where it says that it is equal to.
Okay.
All right?
So just graph it at that.
Graph it at that spot. We don't jump it anywhere because that's where the boundaries are. The boundaries are occurring at that value of x, at that domain.
For the test next Tuesday or Wednesday.
Yeah.
You get to use our calculator.
Yeah. There will be, and that's a good question, there will be times when we have tests or quizzes that I'll have calculator, non-calculator portions. I don't think this chapter warrants a non-calculator portion. Yes, sir?
All of our early years of math, we were at times told we would not be able to use calculators ever once we got out of elementary school.
Yes and no.
I find that we've gotten these calculators on everything.
There have been instances in specific classes that there are times for calculators and there are times for not for calculators. And if you think about, elementary school when you were in that, like 4 or 5 years ago, philosophies were different. So things have changed, technology has changed and all that. 5 years ago we got our first smartboard, and so you start thinking about that. So, that's kind of stuff we're doing here. Yes, sir?
In addition to that, I think that 4 or 5 years ago, the math we were doing, they wouldn't want us to have to use a calculator.
Correct.
So they wouldn't want us to have to multiply 2 times 2.
Correct.
On the calculator.
Right. And that's kind of one of the good things to say. The drilling that you guys probably got is good.
Wonderful, actually.
Yes, because that way you can do a lot more mental math. And I wish that there was more of that now. Because that way you can do stuff faster. So if we look into the next one here, this one's good. Let's do the one that has 3 of them.
Go.
So in this one, when you graph this one out, you're going to wind up with 3 different graphs. You have 3 different equations there. So it's telling you that something's happening at 0, something's happening between 0 and 5, and something happens after 5. Now, when I go to graph x squared minus 1, I'm not going to use my calculator right now, and I don't know if it's on your phone. Yeah. It's not obvious. You know that, right?
Yeah.
Okay.
Well, wait.
When you're looking at something like this, x.
It's not
He's sitting there like this.
So you mean he is? Yes, at least.
Anyway, x squared minus 1. In this problem here, I know that I'm looking at all values of x that are smaller than or equal to 1, or equal to 0. So I'm just going to go ahead and start with x equaling 0, and I could probably do this one in my head. If x is 0, y is negative 1. And it's a solid dot because it said it's less than or equal to. I'm going to the left, so now I use negative 1, square, subtract 1, I get 0. Negative 2 squared minus 1 gives me 3. And then negative 3 squared minus 1 gives me 8. So the first part of my graph is the curve. The second part of the graph is the 2x minus 1. Start at your y-intercept of negative 1, walk your slope. I think I needed to have that extra up there. I want this one to occur between 0 and 5. Now, in this instance, again, the curve and the line meet at the same point. When that happens, it's okay that it stays filled in. Because as you're getting closer and closer and closer to 0, at 0 you are still on that line, but the very instance that you go above 0, you switch to this, all the way until you get to 5. And then at 5, you're still there, but the second you pass 5, you're at y equals 3. So it's 1, 2, 3, 4, 5. And you continue that way. So you've got a curve down, line, and drop. Yes, sir?
I didn't figure out my calculator and stuff, so I was able to do
Bless you.
most of these in my head.
Yeah.
Do you want us to like try and do it?
Yeah, that's fine. All I'm saying is that if for some of these problems, you should be able to do that in your head, and that's great. But if you've got, you know how the one we had yesterday was x squared plus 2x plus 3? Use your calculator for that. I mean, you can do it in your head. It's not that tough, because you're only bounding around the x and y, plus 1, minus 1 type stuff. So it shouldn't be that bad.
I just asked because it was kind of like Hunter's question. Do you want us to get the actual practice?
I'm not
Does it
gonna-
not matter?
It doesn't matter. When we talk about taking calculators away, it's going to be on stuff that you don't need a calculator to do. It'll be when you graph specific style problems, graphing trigonometric functions. You don't need a calculator for. There's a specific pattern in working with just simple fractions that you work with. Things like that. You'll understand when we get to a point like that. When we do matrices in chapter 4, yeah. We do matrices in chapter 4. There are some matrix operations that we work on that you just press a button, the calculator instantaneously does it for you. But I want you to be able to solve for specific parts of that without the calculator. So we probably won't have any non-calculator part until chapter 4. Yes, sir. Well, he's been on his phone this whole time, so might as well get him so you go back to his phone and text his girlfriend.
I'll have you know that I got 96% on my chemistry.
Congratulations.
Yes.
Taylor, do you have a math question?
I personally did.
I was wondering. So, the third line on the 3,
Yeah.
does that just mean that the one going up dropped down with nothing in between?
Correct. Because the very instant you're on this line of 2x minus 1 until you equal 5. The very instant you are more than 5, you're on another line.
Oh, that's
Okay? So as soon as you're 5.000001, you're over here.
I don't really know how to do the x squared without a calculator.
That's fine. Then use your calculator.
Oh, so you don't even need it.
I'll build it
But
in.
we don't have this.
It'll be built in, and it's going to be something where it's like a cost thing. It's a very simple setup. And I still plan on getting to some of the word problems. We're kind of like a day off right now. We'll probably get to more of that on Friday. Okay? So, but don't freak out.
So yes.
Yes.
Okay.
And when you do those types of word problems, it's not going to be curve with linear. It'll generally be just straight linear. Okay? And let's see, the last one should be okay. So hold on to those, keep those as your notes, but what I want to do today then is jump into the other part of it where it's writing equations. And I have these graphs already made for you as well. So that way we can understand what we're looking at before we try to draw them.
Hey, look what I brought.
Atta girl. This you got it in the door.
What? I missed the insult part of that.
Don't worry about it. So here's what we've got now, guys.
Your eyeball.
Ladies and gentlemen. Yes, ma'am. So here's what we've got going on now. Now we're going to be looking at a graph and writing the equation from that. So we're going to be using slope-intercept form for all of these. And the easiest way to be writing these graphs is to identify where the graph changes. What happens, where does a graph change direction? Where does the graph jump? Remember you guys were talking about jumping that gray area? What values in the domain do the graphs change at? So we have some pretty good easy ways of setting these things up. Let's go one at a time. Now, every one of these types of problems kind of starts the same way. When you're looking at that first problem, how many different directions do they go? Two. There's two of them. So how many equations should my function have? Two. You should have two of them. So that's the first thing you identify. Once you identify that you're going to have two equations for your function, you start with your function notation. F of x equals j leno space.
What? Oh, I get it.
We're at.
Oh my god. It's his nose and then his mouth and then his chin. I think. That is awesome. Oh.
Oh, it's his hair, and then his nose, and then his mouth.
How long have you been able to draw that?
I didn't pay attention to a lot of classes in college, and I just drew brackets a lot. When I student taught, did observations, and I found some teachers that drew really cool brackets, so I just tried to draw brackets, and hence why I can draw that. Don't ask me to draw it facing the other direction. I can do it this direction all day long.
Like you did it really
Fast.
swiftly.
Do it again.
You get more than one problem.
One more time.
Now we've done the f of x notation equals j leno space, and now we know that these things are all domain specific. There are going to be two equations, so what I want to do is know that something happens when x equals less than or something like that. And where is that occurring? What value of x do these graphs change? At 0. I know something happens at 0 for the first graph and 0 for the second. Now, when I'm saying first graph, second graph, the way that you read these things is that you read them like you would a book. You read going from left to right. I read this as it's increasing from negative infinity through positive infinity. So this portion down here is the first graph that I see. So it goes on the top and then sequentially down the line. You could have 3, 4, 5 graphs on here. Okay. So after I do that, I identify that something happens at x equaling 0. I don't know if it equals, I don't know if it's less than, I don't know what's going on yet. But now I go to slope-intercept form. Since we have a nice graph on the grid, all you have to do is walk your slope and identify your y-intercept. Walk your slope. What's your slope? It's 1, so the equation is, and what's your y-intercept?
0.
So I know that the function of x equals, for the first equation, x. I don't have to put in plus 0 or anything like that. Now, if you remember what we did yesterday, we said f of x equals 2x minus 1 when x was greater than something. Put a comma there. When you're done with your equation prior to your domain restriction, just put a comma. It's more etiquette than anything. Where is this graph occurring? Less than 0, greater than 0?
Less than 0.
Less than 0. It occurs less than 0. What happens at 0?
Turns up.
It turns up. It goes to 11. It turns up and it goes to 11. So as soon as it becomes 0, it changes graphs. So as you're reading these things through, normally when you don't see an open and closed dot, you're increasing from negative infinity towards positive infinity. As you hit that inflection point, if you will, it changes. As soon as you get closer and closer and closer to 0, you're on this line. The minute you equal 0, the instance you become 0, you change and you go up faster. So that's why it's less than approaching. When it hits it, it becomes it. Yeah.
Like, can't you just say, like, the minute after, like, say, like, if you start making more money at 9 o'clock, 9:01, you start making more money.
I see what you're saying. It's just the way that things are normally written, it's written in this manner. I know what you mean, but
Okay.
yeah, it's not at that 9 o'clock value. It's when you get to that 9 o'clock, it switches over because once it becomes past that, you're on that.
Oh, okay. That makes sense.
So this is how you separate the graphs?
Mhm.
So, okay.
So now what's the slope of the second line?
Well, it's 2x.
Yeah.
Why can't x be less than or equal to 0, and then x be greater than 0?
It's normally written in this manner, and I see where you guys are saying. Is it completely wrong that if this was when it's less than or equal to, and then it shifts to here? Doesn't that mean the same thing? More or less. If it was a word problem, which I know you're really excited to read, it would be a little bit easier to decipher because it'll say at this point it changes to something else or along those lines. But normally speaking, as you approach it, then you change gears.
That's the real thing.
It's the rule of thumb. It's a standard way of looking at it, and that's how I was always taught. That's how I've always shown. And then, like you guys just said, your second equation, your intercept was once again 0, and all you had to do was just walk your slope, and they happen to be 2. So your equation then is your f of x equals j little space of x when x is less than 0, or 2x when x is greater than or equal to 0. The reason I put the comma in there, because to me that means when something happens. Yes, sir.
What else can you make space out of the bracket?
Let's see.
I just don't think you can make it again.
Probably right.
Oh, got you good.
Bet.
Bet. Bet.
Looks like Tiggelar.
Oh, Barnes. If I had my smart board, I'd get you back at least.
No, I really can't draw anybody else. It's just,
Can you just draw it again? Can you do
I
it?
will, because we have another problem.
Is this our homework tonight?
No,
It isn't?
these are examples. All
I was
right.
hoping it was.
Once again, this is the second one. As you're reading from left to right, everybody sees that there's a jump here. There's an open dot and a closed dot. This is very well defined as far as the domain is concerned. The domain is very easy to find here. What value of x is the domain changing? -2. Good. So we know where our domain's changing. So we start with f of x equals j little space.
That was good.
That was good.
That was good.
It's not as good as the other one. I think the other one's
But
better.
it has, you know, that one's
His lips are a little bit wider.
That one.
He's talking.
Yeah, I never saw you do it again.
Can you do it?
There's no problems.
All right.
Now, look at your two equations. One equation is pointing down and to the left. Is that a less than or a greater than or a less than or equal to or greater than or equal to problem? It's just a less than. And also because it has an open dot. Since we have an open dot here, we know that's a less than. And then I know the other one is when it's greater than or equal to because of the solid dot. So So, next step, identify slopes. First equation, what's your slope?
The first one?
Yeah.
No, that one is something. That's
Remember, we're reading this.
Oh, it's X. Okay, my first one, it's just an X.
Your slope is x. Now you have to figure out what your y-intercept is.
5.
Yeah, all you do is extrapolate the graph. I mean, you could do
5.
when
Count
x
it.
less than 2. All right.
Wait, how do you know it's less?
See how it's pointing down? See how it's pointing towards the left?
Yeah,
That's how it works.
I found that. Should be helpful.
And then one of the things you tend to forget. Horizontal lines all have the equation what? Y equals some number, right?
Y equals X. X is in some number.
And then vertical lines is x equals some number.
So it's just -2, right?
Correct. And that's it. You don't write f of x equals y equals -2. Because remember, f of x is synonymous in using y equals. And f of x is a function. Y equals -2 is also a function because it passes that vertical line test. So you just leave it as f of x is -2. All right. Now,
This one has 3 or something.
it has 3 or something, so how many equations do you think you're going to have to write?
3 or something.
3 or something. Now, I'm going to help you start with the parameters of your domain. And after that, I'm going to have you guys finish these other ones, and we'll check them in a few minutes.
Does your laptop ever get like super slow from all the pages you have open?
You know, the only things that I have open right now is just my computer. I'm running the other browser because I'm trying to upload the videos from earlier, and it just, I can't get it to go any faster. I put this on here 2 hours and 20 minutes ago, and it's still not even loaded. Like, as soon as I get home, I open my laptop up, and they're uploaded in 5 minutes. So. In this case here, remember we have 3 equations. So we have to worry about 3 things that happen.
Dang it. They always look bad.
What's going on domain? -1. I know there's something going on at -1. Now the tricky one. Do you guys remember when you wrote stuff out on a number line? X was between 2 values. See how X is between 2 values with an open dot? That means it's not equaling either one of those, but it's greater than, for this example, it's greater than -2, but less than 1. Here it's greater than -1, but less than +1. And then the other one is something else is happening at 1. I'll let you guys finish out the rest of it. Okay? It'll only take a couple seconds. And then finish the other 2. And we'll check them in a few minutes. I want to bring up one other definition real fast before we get out of here. In this case here, the first graph that we have is a less than or equal to -1. I'm assuming you guys got that okay. The last one was a greater than or equal to because of the solid dots. The first graph has a slope of 1. What is its y-intercept?
Which one is 2?
So it'll be x plus 2 when x is less than or equal to -1. The next one has a slope also of 1. What is its?
Right.
And then last but not least, ¿cómo se va?
C. Oh, 1, 2, 3.
Very good. No es bueno para
No, por favor, señor. No, please. Oh, this one.
¿Tú tienes llaves para su coche?
You're not even talking. You know it. Don't even lie to yourself. Walking around campus like you're the man or something.
In this case here, once again, how many different equations are we going to have? 3 of them. Good. Last hour I got caught up on the plateau part. This is still a part of the graph. So f of x equals j ln space.
Oh, that was really good. That is really good.
You have 3 of them. You have 3 values to worry about. The first value as you're approaching -2. Why am I saying just less than -2?
Can you put that on a t-shirt?
This is the whole thing or just j ln space?
I think the f of x makes it.
His lips messed up on that one.
Is that
He's
It's, you know, I'm not like a Picasso here. Okay?
Yeah, like a big.
That's pretty abstract.
Look at the difference between the two.
Anyway, why is it just less than -2?
Wait, why is it equal to or less?
Remember, as you're approaching -2, as soon as you hit -2, you change. So as soon as you hit -2, you're changing graphs. And then once again, as soon as you hit the next one, you're changing the other way at +2.
Oh, so the end of the graph is the tilde point.
Usually, yes. Because you're reading it going from -infinity to +infinity throughout your domain. So where are you changing? I'm changing at -2. I change again at +2. So I'm increasing. I change at -2. I stay the same. And then as soon as I become +2, I change again and go the other direction. That's what you're looking at those. So if you keep in mind as you're reading from -infinity to +infinity throughout your domain, that gives you your breakpoints. The rest of it should be relatively simple. The first one has a slope of 3. And if you extrapolate up, did you guys get an intercept of 10?
Yeah.
On the other one, it's a y equals a number. I think it's 4. And the last one has also an intercept of 10. What's your slope on the other one?
negative? They're similar lines.
All right. Lastly, the very last problem is fancy. When walking around, I don't think I looked at anybody's paper that got this wrong. This is called a step function. Why do you think this is called a step function? They resemble stairs. So they just call it a step function. There are horizontal lines at different intervals. Sometimes the intervals may be open then closed. In this case, it's closed and open. It just depends on the graph. This one should have been easy. You have 3 of them. 1, 3, and 5. And was it x is
Worse than me.
0 to 2, from 2 to 4, oops, and then from 4 to 6. All right, that's your step function. You see those from time to time. Your book has them in there. They will have like decimals and whatnot as well. The problems I'd like you to do tonight are in the book.
Oh.
You need 1 sheet of graph paper. You need 1 sheet of graph paper, so if you don't have enough with you already, there's some up here. I can just pass more back here. All you need is 1. The other problems are writing the equations. I will explain to you what it means when I said make the y-intercept 10 or -10 here in a second. I'll just let you copy that down first, and I'll show you the problems, because that way it'll fit on your graphs that you have. The problems in the book have it like a +13 and a -14. That's just silly. So you might as well not worry about the scale and just graph them the other way. So those are the problems, and I'm just going to stop recording here soon.